In Chapter 20, we're going to take a look at describing and drawing and then building circuits. A couple of ways we can identify and describe circuits. First of all, we can describe it with words. We're going to start out with a very simple circuit that we're going to have you attempt to build in class. And that's going to be a circuit that contains a light bulb and a 1.5 volt cell. A cell is sometimes a term that's used in place of the word battery. Batteries many times are made up of multiple electrochemical cells, and depending on the number of them, that determines the voltage of that particular battery. So there would be words. A picture of it would look something like this, where I have the battery and I have a wire connecting the battery with one terminal of the light bulb and another wire connecting the other terminal of the light bulb with the other end of the battery. So I have a complete circular path for the charge to flow. Now, fortunately, we don't have to be artists because we use something called schematics. Schematics are symbols that we use to represent when we're diagramming a circuit, and everyone uses the same symbols so that understanding is clear. When you see the schematic of a circuit, you understand what is present. So one way we can represent a light bulb is with a circle and a squiggly line through it. Another way that it can be represented is a circle with something that looks like the light bulb filament in it as well. The next symbol that we use when we're doing schematics is a zigzag line like that. This is a symbol for resistors. We draw all symbols the same, so an easy way to draw is just a line, bunch of up and downs, and then continue. When we build a circuit, we want an easy way to prevent the charge from flowing through it and then allow the charge to going through it without hooking and unhooking it multiple times. So we put a switch into our circuit, and so the way that we symbolize a switch is like that. This would be open. Sometimes you'll see a circle at each end, and then a closed switch would look like that. A battery or a power supply is a series of parallel lines alternating long and short. Switches, light bulbs, resistors can be put into a circuit in either direction, so the current can flow either direction through them. For battery, it is directional. When we identify a battery, we have the side that has the longer lines representing the positive end of the battery, and the line that has the shorter line is the negative end of the battery. Remember, we define current as a flow of positive charge, so for a battery, the current is going to flow out of the positive and into the negative. Electrons will flow the opposite way. Again, we deal with conventional current as the flow of positive charge in this class because that's how it's done generally in this country. So we have a picture of our light bulb and battery setup. If we were to draw a schematic of something like that, it would look like this. We'd want to put in our power supply, and generally when you draw a battery or a power supply, convention is either two pairs of lines or more. You can and sometimes do see it with one pair of lines, but two is kind of the standard accepted value. You could do three sets of lines if you wanted, as the illustration shows. So we're going to connect the battery to a wire, we're going to connect it to our light bulb, and then our light bulb reconnects to the battery. And current flows in that direction around the circuit. The battery resupplies the electrons with energy, so as they flow through the circuit, they have energy. That energy is transferred then to the light bulb to allow it to produce light energy, and then the electrons, without their energy or with significantly less energy, are returned to the battery where they can be re-energized. So the battery acts like a pump. It resupplies charges with energy. One way we can think about it as a water fountain. So if this is my pump, this is acting as the battery. Water is equivalent to electron flow. So there's a reservoir at the bottom. The water is drawn up the pump. As it goes up, it gains, in this case, gravitational potential energy, so that it has its maximum at the top, and then it falls. As it falls, it loses potential energy, it goes back to the bottom and gets pumped back up to the top. Another animated way that we can take a look at that is represented by this diagram here, where our battery is a pump that pushes electrons up a hill so they gain electrical, or in this case, representing gravitational potential energy. They travel along the wire or the conductor with that amount of potential energy, and then as they fall, they push this wheel around, and in pushing it around, give up their energy to make the wheel go around. So they're turning electrical potential energy into mechanical energy. They end up down here through another conductor where they have much less potential energy, come back to the pump, and they are re-energized. So here's a picture of that diagram in motion. The little spheres are the electrons. The battery is energizing them by giving them more potential energy. They travel along a conductor with a high amount of potential energy. They travel through a resistor, a light bulb, and cause that object to do something. Energy is transferred from the electrons to that object, and then they travel back through another conductor having very little to no electrical potential energy and return to the battery. So in the circuit shown, those charges are going to move this way around the circuit. Here is where they have a high amount of electrical potential energy. Here is where they have a low to zero electrical potential energy. We can arrange resistors in a circuit in either series or in parallel. If resistors are in a series, then we have a single loop. So essentially the resistors are attached end to end, connected by wires, and we have one loop that is formed that includes the power supply of the battery. If this is the case, the current is the same everywhere throughout the loop. Remember, current is the flow of charge per unit time, so I've got the same number of electrons per second traveling through any section of the circuit. When I have a series circuit, the equation for it, taking Ohm's law, looks like this. I add up the voltage of all the resistors, and that equals the voltage of my circuit. So that's the voltage of resistor 1 plus the voltage of resistor 2 plus the voltage of resistor 3, depending on how many there are. And this voltage of resistor 1 is the current, because it's constant, times the value of resistor 1 plus the current times resistor 2 plus the current times resistor 3. So if I wanted to find the effective resistance, or the resistor I could put in, a single resistor I could put in place of all the resistors and still get the same voltage and current, the effective resistance is just the sum of all the resistors in the circuit. It's also referred to sometimes as the equivalent resistance. Again, the equivalent resistance is the sum of all the resistors in the circuit. If I were to draw a schematic of a series circuit, it would look like this, or something like this. So there would be a circuit, resistor 1, resistor 2, resistor 3. My current is traveling this way around the circuit. The other way I can arrange resistors in a circuit